Good afternoon. I am your host, Andrei Bartic, Cluster Manager at Flanders Make. In my name and in the name of my colleagues, I welcome you on the Heurisko webinar on mobile working. For the best experience, we recommend you to use a fixed internet connection. You will have the opportunity to post questions via the Q&A section, and we'd like you to pose these questions during the presentation. Also, give your first and last name so that you know who posted the question. Unfortunately, we will not be able to handle all the questions during the session. If you have questions that did not receive an answer, we will get in touch with you afterwards. We would like to start this webinar with a short poll in order to get to know each other and in order to get to know the companies that are participating to the webinar. To that end, we have prepared an online poll consisting of 3 questions. These polls are anonymous, so we do not know who fills them in. Therefore, we would like to ask only the participants that work for companies to fill in these polls. For my Flanders Make colleagues that are listening, we are asking them to refrain from using the poll. And of course, if they have questions and remarks, they can contact us directly. You can scan the QR code on the screen to open the poll. And there are 3 questions in the poll. I'll read the questions. The first one is, which applications do you have for autonomous mobile working? And you can choose from a list of different applications. The second question is, which role can you play in the value chain of autonomous mobile working? And again, it's multiple choice question, so you can choose from different possibilities. And the third one is, in how many years autonomous mobile working will play a part in your application. We will not make public the results of the poll immediately, but we will analyze them and we will make them public after the webinar. I'll wait for a few moments to give you the time to scan the QR code and then take the poll. So again, it's a poll only for the participants that are working for companies. There are 3 simple questions with a number of possibilities for answering each question. Okay, so the responses are coming in. I think thank you very much for your responses. I think it's very interesting information for us, and we will analyze this, as I said, afterwards. So we will continue with our webinar, and I will give a short introduction followed by the 2 presentations. The autonomous vehicles, they come in many different shapes and sizes, and I try to illustrate the different possibilities on this slide. They can range from autonomous drones to autonomous boats to all sorts of manners of land vehicles. They can also have many different applications, from surveillance to agriculture to logistics to automating household chores. And some of these autonomous vehicles consist of a combination of a drive and work function. And I have tried to illustrate this on the slide. Of course, it's just an example of a drive function, which is in this case realized by a tractor. that can be combined with work functions that are realized by the different implements that are illustrated on the slide. Of course, such a combination raises a number of challenges. One of these challenges is how to design a modular and flexible architecture, since the drive function can be coupled with many different work functions. And a second challenge is how to guarantee safety in all these situations, since each implement comes with its own specific safety issues. These are topics that will be discussed in the second half of the webinar. So the second presentation will cover these topics. In the first half of the webinar, we will address a very common need for autonomous vehicles, namely how to plan the motion. And this is typical for all autonomous vehicles because they have to drive to a destination, and the trajectory towards the destination has to be planned. But typically the environment is very dynamic, for sure in industrial environments, and these trajectories have to be adapted in real time to the conditions in the field. And the examples on the slide, you can see an AGV that has to pass another AGV in a narrow corridor. It has to avoid obstacles, and it has to drive forward and reverse. So as I have already anticipated, we have two presentations. This topic will be covered in the next presentation, which is on optimal motion generation, which will be presented by Joris Gillis from Flanders Make, together with Jeroen Bridelance and Bram Vanseveren from Bekaert. And now I would like to give the word to my colleague Joris Gillis.
Thank you, Andrei. Good afternoon, everybody. My name is Joris Gillis. I'm a postdoc at Flanders Make, KULeuven. So in my presentation, I will talk about the theory of motion planning and some concrete solutions that we've engineered at Flanders Make. So what is motion planning in a very general setting? It's the art of going from a point A to a point B. And the thing is to do this transition efficiently or optimal. So what kind of vehicles are we talking about? It could be forklifts or boats, or maybe a more complex model with a trailer. It could also be quadcopters, like 3D space. It could also be joint space of serial robots. So in general, some space of going from A to B, but let's now just visualize this screen as like a top-down view of a warehouse with a forklift. So what are some ways to go from A to B? You could do it rule-based, like very simple and ad hoc. Let's just start at A and drive directly towards B. And then the path consists of a straight line. But then, of course, you could hit an obstacle. So the red circle would be an example of an obstacle that you can detect. So when you hit the obstacle, you could say, okay, I just go sideways for a couple of meters. And when I'm done going sideways, I go towards the goal point B again. And you could repeat this fashion, this rule, and in the end, hopefully you end up at place B. So a very ad hoc rule-based way to go from A to B. What are more structured ways? There are like two big optimization-based approaches. And the first is like discrete based. So what you do, you have this wide open region between A and B, and you just sample it randomly or uniformly. And all the valid locations that are not inside the obstacles, you can connect in a graph. And then you basically apply the graph search algorithms that you find in your GPS or on Google Maps, and you just find the shortest paths between A and B on this edges of this graph. So that's discrete based. Now the things I will discuss are continuous optimization based. So we have this wiggly line is the trajectory that brings us from A to B, and it is like parameterized with three sliders, A, B, and C on the left of the screen. And by picking the correct A, B, and C, or a concrete A, B, and C, we have one concrete manifestation of this blue path. For every blue path, we can compute the length, and it makes sense to desire finding the shortest path. So we can do this mathematically. We say our path length is really a function of A, B, and C, And then you could write, okay, let's minimize this path length. And the degrees of freedom are, as I said, A, B, and C. The only thing you have to take care of is the obstacle, so make sure that the distance between the path and the obstacle is positive. And for a human, it's already quite difficult to do this with 3 sliders. But as we will see, for software, it's no problem. So what we will use a technique called gradient-based optimization to solve this problem. And later on, I will go to software on a higher level. So what can gradient-based optimization do in this case? You give it an initial guess, which would be just a straight line to A and B. And then with just a couple of minor adjustments, you get to the exact optimal solution. So this is the initial guess. This is the first iteration. So that's a numerical process thinking that the intermediate solution is this one. You do a second iteration, third, fourth, and with the fifth, you already get something very optimal. So it's almost straight for a while and then edges over to the obstacle. So this is quite nice that a numerical software can find this in only 5 steps. And the power to do it is really in the ability to take derivatives or sensitivities of your objective, your goal, with respect to these parameters. And this, in the packages at Flanders Make, we use a software called Casari to do this. So this computes the derivatives that are needed for efficient solving. So now in this case, the number of optimization variables were only 3, but it could also be 10 or 100 or 10,000. And typically the iteration number stays rather small. It doesn't grow unbounded. So what can we do with this framework? Well, we hope to do motion planning. There is one extra aspect in motion planning, which is the timing. So typically you subdivide the task of motion planning in 2 parts. So first you plan like the geometric path, the blue curve, and then you plan how fast you will traverse this geometric path. So in this case, the vehicles called V1 and V2, they follow the same geometric path, but they have a different speed or motion profile. And the techniques we use at Flanders Make, they can do it separately, but can also combine these 2 steps and get a more optimal solution. Another aspect is that you can bring in the mechanics of the model of the vehicle you're using. And this I will demonstrate with another software tool that we built on top of the previous one. So in this case, what we're going to do is set up an optimal control environment with a free running time. So we don't know in advance how long it will take to go from A to B. We keep it free and we optimize it for it. So we find the shortest time path. And then we're going to model the system with states and controls. So our forklift has actually 3 states. So 2 for position, so the X and Y position, and then it also has a heading, of course. These are the states of our system, and the controls, the degrees of freedom we can play with are the speed of the vehicle and the steering angle. And if you do things right, the optimal control, when you solve it, it will find the steering trajectory and speed trajectory that you have to apply on the system. You can apply this in real time and it will follow this trajectory. Model is good enough. So we need some kind of prediction model. We typically do it with a differential equation. It could come out of MATLAB Simscape, for example. We can set as many conditions, boundary conditions as we want. In this case, we want to end up at B. And there are also some things that should hold during the whole trajectory, and that is, in this case, of course, the obstacle constraint. So this gives you a mid-level way to specify optimal control problems, which are used to find optimal motion trajectories and the controls needed to implement those trajectories. When I talk about optimization, historically, not everybody has been doing this in the most efficient way. So what you typically see when people are first using optimization they use unconstrained optimization and they put everything in one objective. And let me demonstrate how this makes things difficult. So for our problem, we could say, okay, I want to minimize the time, so go as fast as possible. But there might be some path that we want to stay close to. So we don't use all the free space, we want to stay reasonably close to a prescribed path. And you could do this by adding a term in the objective and you give it a weight, W1. Then another engineer comes in and says, okay, we have to be careful with power, our battery is only limited, so okay, we add power to the objective. And then there are the obstacles, and somebody invents a way to represent that you have to take a distance from the obstacle, you give it another weight. In the end, you end up with really a tuning nightmare. You have all these different weights, and depending on your system, on your context, you will have to retune and retune these weights. It's not a nice situation to be in. What you should really do is exploit the fact that you can have constraints in optimization problem. So instead of saying promote staying close to the reference, just say how close you want to stay. I want to stay within 1 meter or 1 centimeter or 1 millimeter, and let the solver figure out the rest. For the battery, maybe you say the battery has to stay alive during 1 shift of your factory workers, and it doesn't matter if there's more or less battery power left after that shift. Also, you just have to make sure that you're a safe distance away from them. So all these mathematical techniques, they are really nice to specify optimal control problems, and then we built an extra tool that uses this for real motion planning applications. So this tool looks a bit like you first specify the task or the problem, so we're doing a point-to-point motion. You can make a selection of different AGVs, so for example a differential drive, you add it to the problem. You can add one or a lot of obstacles, and then you really have the control loop that you can implement online on your system. So you could say, okay, for every instance I look at my camera or my sensors and I update the current obstacle positions, and I also look at the sensors of my own vehicle and I update the position where I am currently. Then you ask this mathematical problem to be solved, and you find the steering angle and the velocity that your AGV should do in the next portion of time in order to make an optimal motion. And this is what you actually apply, and you keep doing this, and what you get is an optimal way to go from A to B. Now this tool is obviously built on the previous one, so all of these are toolboxes on Flanders Make. So on the OMG tools, which stands for optimal motion generation, you work with vehicles and tasks. Then you go a layer down to rocket, and that works with states and models and control trajectories. And then on the bottom you have Casari, which is really playing with these sliders. On a more high level, you could say you have motion planning is based on optimal control, is based on nonlinear programming. And these are quite modular packages. They're not only used for motion planning. That's a nice thing. They have like foundations that can be used in other disciplines. We use Casari for code design, also for extended Kalman filtering, and we use Rocket also for system identification and for drone racing. So we like kind of the structure where each layer has its responsibility, where each software has its responsibility, is well tested, and has many use cases. So why am I telling you all of this? Perhaps you are thinking at this point it might be a waste of time for my engineers. Perhaps, let's see. Things that are developed ad hoc or rule-based, they typically don't need a lot of engineering time. So if I plotted this technology on the scale, you don't need a lot of time. If you go for optimal control or MPC with this OMG tools or with other tools, it will require a large investment in time from your engineers. But the thing is, this is only true when your systems or your tasks are very simple. So if you're a company designing cleaning robots, maybe all of this is overkill, and a random walk in the environment would be enough. The thing changes when you have the access of complexity. Like you get a forklift is a bit more complex, or you might have things that evolve over time, and you can use preview, or you can have a system with a trailer, or you can have drones or robots. So on this bottom axis, you get more and more complexity, or more desire to have more optimality. And optimality would translate in throughput or in economic advantage. So my argument is that if you stick with rule-based or ad hoc techniques, you would quickly go up, maybe hit a brick wall, while with optimal control, optimal motion generation, you start high but you stay low. And the conclusion would be, if you plan to make a leap in innovation of your products, going from simple products or simple contexts to more complex, then perhaps you should also reconsider the technology that you're currently using for making motion planning. If you don't use it, in the end, if you don't want to bother your engineers with it, you can already use optimal controls vocabulary to just formalize what a good motion task is, and it makes it very easy to communicate with engineers in other fields. With this, I'd like to thank you for your attention and shift to Jeroen and Bram from Bekaert, who are going to talk about applications of optimal motion generation.
Thank you. Let me first share my screen. So I'm Jeroen Bridelance from Bekaert Engineering. I will talk about our story during this project. First, I will talk a little bit about the AGVs at Bekaert, and next my colleague will take over regarding map refinement and interaction of narrow lanes. So my name is Jeroen Bridelance. I'm an automation design engineer at Bekaert Engineering in Belgium. I'm responsible for all the advanced AGVs that we have within Bekaert, and these are AGVs which are combined with XYZ industrial 6-axis robots. Also, my colleague will talk over here, that's Bram Vanseveren. He's responsible for industrial IT and is a software engineer at Bekaert Engineering. He is designing and implementing the planning algorithms, as well as taking care of the host software within Bekaert. So talking about automation in Bekaert, we started with AGVs, and there was one major goal, that was to improve ergonomics and to automate heavy labor and intensive work. If we give, as an example, our average plant, within a year, an operator needs to do, or all operators need to do 20 million of operator material handlings a year, which is quite a lot. So therefore, we started up with a robot and handlings team, which had two subdomains. So one being logistics, where we look at moving spools or pallets from A to B with AGVs. These pallets can range up to 2 tons. But we're also talking about moving spools, and we're not talking about a little package of biscuits. We're talking about heavy spools, ranging from 12 kg to over 1 ton. So quite heavy work. Currently, we are already running 50 AGVs, or more than 50 AGVs worldwide in 6 plants. Another domain within the robot handlings team was the robotics team, which is automating the wire manipulation. And as an example of that, we're currently hot swapping spools, which means that we cut heavy wire while the machine is running, when the spool is full, and we wire up the next empty spool without stopping the production. For that, we started using mobile robots. First, we went for robots hanging on a gantry or moving on rails. But later on, because we have a lot of machines and a complex environment within the Bekaert plants, we started to build those mobile robots on top of AGVs. And because of this, we have a lot of AGVs, and this require good navigation of this in AGVs. Then looking at the navigation technology that we use, this is the only part of the AGVs that we do not develop at this moment, or did not develop at this moment for Bekaert. we used off-the-shelf products, that being the NDC8 platform of KULeuven. It has some pros. It is highly reliable and is well known to the industry. But there are also negative points as well, being that AGVs need to drive on fixed segments, so you cannot move away from this fixed segment. This means that we can do no obstacle avoidance or collision avoidance when we started the project, and also no map refinement is possible. With that, what I mean with that is that if we know that spool is always 5 centimeters to the left and we want to pick it up, there is no possibility to learn the system that the spool is always 5 millimeters or 5 centimeters more to the left with the system. Now I will give the word to my colleague who will talk about those two negative points about the system.
Okay, I'll share my screen as well. Voilà. So as Jeroen said, automatic map refinement and automatically driving around obstacles is not part of the KULeuven software, but still we needed these functionalities, so we decided to build them ourselves. If you look at the vehicle you see on the left, you see a lot of spools laying on these machines. How it works in reality in this plant, an operator sees that a spool is finished, he gets it out of the machine, puts it on the table, and then he scans that spool to let the system know that that spool is ready for pickup. So at that time he registers in the system that a spool is ready on machine A. So machine A is a logical position. If we want an HGV to automatically pick that spool up, we need to translate that logical position, machine A, to a physical position in the plant, which are just XYZ coordinates in the space of the plant. This mapping from logical position to physical position is called teaching in. So all of the possible positions where a spool can lie in a plant, all of these positions need to be taught into the system. It needs to be quite precise. We need an accuracy of more or less 1 centimeter to be able to pick the spool perfectly. So that's a lot of work. You could think, in theory, that this is a very simple problem, and in theory, you're obviously correct. All our machines are standing in long rows. So if you measure the position of the first spool of the first machine, and you know how far your machines are apart from each other, for example, 2 meters, then you could extrapolate that position by just adding 2 meters, for example, in Y direction. In theory, that would work perfectly, but in practice, not all of our plants are brand new. There are sometimes old machines. Sometimes the machines are not exactly the same. So this extrapolation does not work at all. All of this teaching in the past, it was done manually, and it is a lot of work. So for every position, you first start from the theoretical value, then you let your vehicle pick up these spools, and every time it fails, you try to estimate in what direction it fails, and you make a slight shift in these values in the system, and then just try it again. Another problem is that these positions tend to drift over time because these machines are old, they move a bit, and not all of our vehicles, not all of our AGVs are perfectly the same. We try to tune them and calibrate them as good as possible, but in reality, they are never exactly the same. So these XYZ coordinates, it would be really good if they would be unique per vehicle. All of these things were not possible in the system, and the teaching in took a lot of time. So we added software and sensors to the vehicle. So the vehicle was able to detect the position of the spool. So the vehicle first drives to these XYZ coordinates that are registered in the system, the theoretical value. Then with its sensor, it detects where the spool is. Then it moves a bit forward or backward or extends its arm a bit more or less, and it picks the spool. So with that solution, it seems that all of our problems were solved. The teaching in did not need to be that exact anymore because the HV could make corrections. The problem with these corrections is it takes time. The vehicle needs to move a bit, needs to detect the spool. It takes time. It's not a lot of time. It's some seconds per spool, but if you know that in some plants we pick more than 4,000 spools per day, these some seconds become a lot of time. So we decided to build an extra software layer on top of that. You can see it here in the diagram. So we start with step 1. The vehicle is sent to the XYZ coordinates, which is the theoretical value. The vehicle drives there, and the vehicle detects the spool at slightly different coordinates. Let's call them x2, y2, and z2. The vehicle, of course, picks the spool. And then a very important step, step 4, the vehicle sends back the offset. So it says I did a correction in x direction of 50 millimeters, in y direction of -5 millimeters, and in z direction I did a correction of 0 millimeters, for example. This information is sent back to the host system, and in the host system we keep it in a database. So for every logical position, we keep the physical position per vehicle. If the vehicle sends back these outliers, we update that position. What we do, we first detect outliers. If the vehicle sends a value back to us that is really, really different from all the previous values, it's probably a sensor glitch or an error in the vehicle software somewhere. So we discard these values. And then if we accept the value, if the value is okay, then we take a sliding window average from with the last values. For example, the last 3 offsets that that vehicle sent back for that specific location, we take these averages and we update the position. So next time the vehicle drives there, we will send these updated values to the vehicle. So the vehicle will, in normal circumstances, will already be positioned correctly with these updated coordinates and will be able to pick the spool perfectly. So this way we have unique coordinates per vehicle, per location. That's what we wanted. And as a second one, the corrections that the vehicle will have to do will be very small. So we gain a lot of time. And as a third one, the shifting of these coordinates due to wear and tear on the vehicles and on the spool positions, we also account for that because these coordinates in the system will slide along, will drift along. So the problem of that teaching, and it was very hard, was solved automatically. We just let the system run for 2 weeks, and then the picking is optimal and will stay very close to the real values. Another problem we had in our plans were interactions in narrow lanes. So if you look at the diagram, you see that our machines are organized in long bays. So on top and on the bottom, you see the blue boxes with TU. That means take up, and that's a position where a vehicle can pick up a spool. These bays are wide enough for 2 vehicles to drive next to each other, but they are too wide for 1 vehicle driving in the middle and picking on both sides. So if a vehicle arrives, he has to pick a driving lane, the top one or the bottom one, and can only pick on that side. The vehicles also always drive in one direction, in this case from the left to the right. That's just for safety, because an operator then always knows where a vehicle can come from. And with these types of vehicles, they pick a lot of spools in one bay, up to 15 spools, and then they drive to a palletizing robot for unloading. The problem is, of course, that on the bottom, these 2 vehicles drive behind each other. If the first vehicle is slightly slower than the second one will be blocked a lot of the time because he cannot pass or overtake. Also, if an operator is working in that bay, the vehicle will also be stopped. So that's a problem. We asked Flanders Make to do a simulation with our specific vehicles to drive around an obstacle. You see it in the movie on the left. So what does the vehicle do when he detects an obstacle? He drives backwards, he drives around the vehicle, then he has to drive quite far to become parallel to the machines again, because to pick a spool, he needs to be parallel to the machines. And then he drives backwards again, close to the obstacle, to make sure that he hasn't passed a lot of machines, because on these machines, he needs to pick spools. If you look at it realistically, we see that it is not efficient. Our vehicles, our current generation of vehicles, these vehicles are quite long. The driving is very inflexible. So we decided with this type of vehicles not to drive around obstacles. It's a huge loss of time. For our next generation of vehicles, we're looking into way smaller vehicles that are more flexible, that have more steering wheels, because our current generation only has 1 steering wheel. When we have that new generation in place, then we will, of course, look into this driving around obstacles again. So we could not solve our problem with this solution, it was clear. So we decided to go for a different route. We have a planning algorithm that decides which HV will pick which spools. We decided to write a completely new planning algorithm from scratch with some extra requirements. The first requirement was that we wanted to make it very efficient. So an AGV would only drive through a bay and pick spools there when it could pick a lot of spools. So a vehicle can pick up to 15 spools. So let's say we only let it drive to bay when it can at least pick 12 spools. Or, of course, when it is urgent. Every spool needs to be picked before a certain deadline, and that deadline is when the next spool in that machine is ready. So a spool is laying on the table. When the next spool is ready, the previous one, of course, cannot be on that table anymore. So a vehicle will only drive through a bay when it can pick a lot of spools, or when it becomes urgent. We call that just-in-time picking. And a second requirement is a vehicle should avoid bays where other vehicles are already present, because that would lead to annoying interactions. So we developed an algorithm with a scoring system. So the algorithm has five parameters that influence the score, and each of these parameters has a certain weight. So that defines how big that influence on the total score is. So if an AGV has nothing to do, he will calculate the score for every bay, and then he will decide what bay to drive to. If the score is too low, he will not drive to any bay. If the score is high enough, he will drive to the bay with the highest score. The parameters that influence the score are the deadline and how urgent do this spool need to be removed from these machines, the driving time for that particular AGV, so the driving time from the AGV to that particular bay. It's more or less the same as the distance, but driving time is more interesting because taking turns takes more time, but is not a big distance. The third factor is fill. How full will the AGV be after he has picked the spools in the bay? The fourth one is empty bay, is how empty will the bay be after the AGV left the bay? And the last one is traffic. That means how many other AGVs are already in that bay. Of course, if we look at the second requirement, we make that traffic factor very important. We give it a very high weight to make sure that we avoid two AGVs going to the same bay. Of course, in very extreme circumstances, it is still possible that two AGVs go to the same bay. It's only a score. But in extreme circumstances, that is the best solution. So we don't care about these very extreme circumstances. They almost never happen. We implemented this system. So in 2016, we had the old algorithm. In 2019, the new one with the scoring system. If you look at the block time, so the time an AGV is not able to do useful things when he is standing still for another AGV or an operator, it used to be more than 7%, and it dropped to less than 3%. That does not seem that extreme, but if you look at the number of spools we pick 1,000 spools more. So in 2016, we picked 2,600 spool, and now we picked 3,600. So a drop in blocking time and picking way more spools, that proves that the algorithm works and the results are quite well. So interactions with other AGVs, that is solved. The only one that remains is interactions with operators. We had a very simple system for that. We installed at the beginning of the bay a push button and a colored light. If that light is green, it means an AGV can go and pick in that bay, and that no operator is doing a lot of work there. If an operator needs to do maintenance to a machine or needs to weld something, then he pushes the button, the light becomes red, and that's an indication for the AGV that he cannot go in that bay and pick spools. When the operator is finished, he pushes the button again, the light becomes green again, and the AGV can take that bay again into account. That was it from Bekaert's side. Back to you, Andrei.
Bram, thank you very much for this very interesting presentation. I would like now to continue, so I will let me share my slides again. And as an end to this first session of the webinar, I would like it to fill in a second poll. It's again a poll only for the participants that were for the companies. And if you scan the QR code on the slide, then you will reach the form where you can answer this question. There's only one question asked, and that is, will you be interested to test the open source OMG tools? I'll give you a moment to navigate and to fill in your answers. Okay, the answers are still coming in. Okay, I think we can continue with our webinar. So as promised, in the second half of the webinar, we will address the issue of modularity in autonomous vehicles. And this presentation will be given by Chris Ganseman from Flanders Make and Bart Lenaerts from CNHi. And now I would like to give the word to my colleague, Chris Ganseman.
Good afternoon. My name is Chris Ganseman from the Flanders Make Motions Lab, and I will present you today our autonomous working tractor that we realized within the off-highway project. So first, an introduction on...
Chris, you still have to share your screen. Thank you.
Okay, sorry. I will first give an introduction on off-highway autonomous working. What is it? And here you see a picture of a tractor where actually the cap has been removed. Question is that the end status of off-highway autonomous working in agriculture? And I will explain based on our own tractor how far we are in realizing that type of application. And I will mainly explain that based on the building blocks of the Flanders Make tractor that we have built. So we have on one side the sensing block that gives us real-time information on the tractor and the environment around the tractor. And that is combined with information from the knowledge base, which is information that has been captured from the past, and that is used by the processing module to come to valuable information that is used to control the whole system. Output of the control system, it's coming out of the processing, is then sent to the activation module that actually drives the different actuators which are on the tractor. And then I will explain how far an operator is still interacting with the vehicle, and how also the interaction between the vehicle, the infrastructure, and the communication towards the overall environment is done. And I will give you an idea about the future of autonomous working as we envision with this vehicle. I will first explain on mobile working, what is it, what is specific for with it, and also point out some of the differences that we have with autonomous driving as we typically know for passenger cars. The focus in mobile working is on the work function, because that is typically where the economic added value is generated. Whereas for autonomous driving, that's really focusing on transport of persons and goods. In that case, for autonomous driving, you typically will avoid any contact. Whereas for mobile working, we really need to get in contact. We need to get into contact with the object we want to manipulate. What is similar for both cases is that there are obstacles we want to avoid. In a field, there will be few, because basically if you would have a tree in a field, the farmer will remove it. For autonomous driving, however, especially if you're driving around in an urban environment, there will be many obstacles and they will typically be very dynamic. Mobile working will typically be executed as a lower speed, whereas autonomous driving, especially on a highway, you will have much higher speed. That has influences on how far you have to see, how far you have to perceive the environment, how big you have to make your safety zones around your vehicle. There are very huge investments at the moment by many players for autonomous driving. There are investments in technology, investments in hardware and software. A lot of data are captured by millions of kilometers test driving. For mobile working, the investments are much more limited. But of course, a lot of technology, hardware, software can be taken over from the autonomous driving. What is new and what you need to redo is this capturing of data, because the environment, what you are doing, is different than in autonomous driving. So that is something new you have to add. If we look to the pure autonomous functions for agriculture tractors, we already know about 20 years of precise GPS steering, which means that the steering wheel is automatically moving and turning so that you can follow a predefined GPS track. That typically is not yet there for autonomous driving, but gradually we see other elements which are added, like better speed control, which increasing the autonomy levels for autonomous driving. If we look to the tractor, actually it is on one side a driving platform, but on the other side it also provides mechanical, hydraulical, eventually electrical energy to your implement. And the way how this implement or work function is connected to the tractor can be done in different ways. Sometimes it's completely fixed, which means that the kinematic motion of your tractor is fully defining the motion also of your implement. It can be a towed implement where actually the history of how your tractor has been moving is defining where your implement is. In some cases, you even have a fully integrated work function and driving function in a self-propelled vehicle. And if you look to the degrees of freedom in the overall system, there are different levels of degrees of freedom which are added by the implement to the driving vehicle. In plowing, you just have 1 degree of freedom. The plow can be lifted or put down. For a front loader, you typically have the lifting or lowering of the front loader, but you in addition have the tilting of the bucket. For a mowing arm, you can lift it, but you can also stretch it further away from your vehicle, and you can tilt your mower, which are already 3 degrees of freedom. And if you're adding work functions implements on the back side, but also on the front side of your tractor, you still have more degrees of freedom. So all of these functionality we want to be able to control. And if we come back to the main building blocks, a first block there is the sensing. And you have sensing with different objectives. First, you have the sensing for your work function. In this case, we want to work with a front loader, which means we want to see the object we want to manipulate. In this case, this is implemented by 3 LiDAR sensors to detect a pallet. So this LiDAR sensor works on an emitted laser pulse, which is reflected, and we can measure by that what is the distance. So we obtain a point cloud with distance and intensity towards objects in the neighborhood, including the pallet. And then in the processing that we do with those data, we have clustering of points, and we can detect the opening in the pallet that we need. This is still an expensive sensor, but as higher volumes of this type of sensors is coming in the automotive world, the price for this is rapidly decreasing. A second sensing functionality we want to have is to detect obstacles. In this case, we have a radar and a camera combination that we use, for instance, to detect two persons walking beside the tractor in a field. The radar can give us the position and the velocity of those objects. The camera we use for classification, for instance, to say, oh, what you see there is a person. And then for processing, in this case, we need a quite high computational power by an NVIDIA Drive PX, which is also typically technology used for autonomous driving. And we use that to recognize that the objects are persons. In this case, the knowledge base is a trained neural network. So it has been trained, for instance, for persons, which means that for mobile working, if we want to recognize other objects, for instance, the crop or stones or holes that could damage our implement, we will have to capture new data and we will have to retrain neural networks. And then the third functionality for sensing is to know where we are. And that we have realized on our tractor by implementing a standard GPS RTK system, which is basically using information from all global navigation satellites and using also fixed references. That gives us 2 centimeter accurate position of our tractor. And the knowledge base that we can use here is a map of the field, which we eventually have built up in a CAD system, or that we have been building up by historical information from driving over the field. Now that we have all the sensor information and by the initial processing have already turned that into valuable information, we can go to the next steps within the processing. On one side, that's high-level planning. For instance, first decide to go to a certain GPS position, which is bringing us a motion along a defined path with its own longitudinal and lateral control. And then once we are close to the object we want to manipulate, go to a work motion planner, where we have both the motions of the tractor that we have to control, for instance, first aligning well versus the pallet, and then next operation where we, for instance, move the front loader and lift off the pallet. During that task execution, we still have to keep in mind that if we see an object which is in the way, we either have to stop for the object or restart the planning and replan the whole path and follow a way around the obstacle. Once we know how to control, we of course need to bring those signals to the actuators which are on the tractor. We have 2 different ways to do that. One is by sending the proper commands over the vehicle CAN network. On one side, for the working control, that's the lifting of the front loader, but also, for instance, starting the PTO so that we actually can bring mechanical energy into our work function. But also sending the necessary commands for the vehicle control. That means the commands for the steering, for the throttle, for the gearing up or down. If we cannot do it over the vehicle CAN network, we also have a system which can be built upon the steering wheel, upon the available pedals, so that by mechanical activation of those operator interfaces, we can also bring commands to vehicles who do not have the type of electrical control. And then the current situation is that purely for safety reasons, we do not want to have an unmanned cab. So we always have an operator in the cab who, instead of still operating the vehicle, is just monitoring how the different processes are running. We have on board quite large data storage. As I explained, you at certain moments need a lot of data to be captured to be able to train some of the artificial intelligence systems on the information that are typically available in the working environment. We have a point-to-point communication for remote monitoring and control by other persons outside of the tractor cab. We have an own battery system, which can provide the whole control system with power. And everything has been materialized in boxes and into portable systems so that we can put it on various vehicles. So this is an overall architecture. We have the sensing units, we have the perception pre-processing computer units. And then we have on one side a rapid prototyping software for rapidly manipulation of additional perception information. And we have a rapid control system, which allows control system engineers to very rapidly make controllers, for instance, in Simulink, and then make that into an operational program that we can download to the tractor. And there we also have a lot of interfaces, communication, INO protocols that we on one side can use to add additional sensors, but also can use to control drives and other actuators on different vehicles. With this realized mobile working platform and tractor, we want to support Flemish companies working on autonomous mobile vehicles, not only in the field of agriculture, but also on logistics, but as well construction works, mining and forestry. The front loader operation is typical for logistical and agriculture operations. We also want to further develop the use of artificial intelligence, for instance, better understanding what's happening around the vehicle, faster learning with less data, and also learning to execute more complex tasks in a very natural way. And as we have this the working and driving to work together from an architectural point of view, it's not always clear yet how these have to work together. So the question is, how can you best build up your total system in a modular way on the levels of sensing and perception, on the levels of motion control, but also at the level of safety. And I now want to give the word to Bart Lenaerts from CNH, who can give you a view from the industrial side.
Thank you, Chris. I'm Bart Lenaerts, project lead at CNH Industrial. First, a small introduction. Agriculture today is facing a number of important challenges. This is a report of the Club of Bologna of 2018. As you can see, we have a strong environmental impact. We're using 70% of the world's fresh water, and we're emitting 25% of the world's carbon dioxide in agriculture. In the future, we'll have to feed a growing population, 9.6 billion people, at a lower cost with a lower agricultural workforce, among which a lot of inexperienced seasonal workers, and with the use of only 4% more arable land. In the last century, we have seen a stepwise technological introductions, all with the aim of a sustainable intensification of agriculture. And today we're in what we call the fourth agricultural revolution, characterized by a strong increase in automation. Why? We see three strong opportunities for highly automated agricultural machines. First of all, in labor availability. As our machines are growing bigger and more complex, more and more the operator becomes the actual bottleneck in the increased productivity of the machines. And what we want to do is to automate the dull and the dangerous tasks. So the operator can concentrate on key tasks that require more experience and more awareness. And we can transfer potentially unhealthy activities to the autonomous system. Secondly, we see advantages in productivity. Automation, of course, aims at an increased utilization of the installed capacity. It achieves a more uniform productivity throughout the working day. And we see an increased accuracy and repeatability of activities, which leads to an increased yield and a more efficient use of resources. Furthermore, we see a better integration through more connectivity, which can lead to an overall optimization of the entire farming operation, also incorporating information on traffic, on weather conditions, even satellite data predicting when a certain field can be harvested. Lastly, we see an advantage in operating costs. It can lead to a reduced downtime and a total cost of ownership through a more smooth operation. At CNH, we have a clear vision on what we call autonomous or highly automated machinery. We defined 5 levels of autonomy based on the ASAE standards, on which we will launch incremental operator assist functions, which will prioritize based on customer value. We have a global core components R&D team, but the requirements come from the product groups. For instance, in Zedelgem, we are a center of excellence in certain harvesting machinery. We provide the requirements for our machinery as we have the product specialists. But our group in Zedelgem also needs to be prepared for a future when autonomous systems need to be integrated with our current systems. We see some key areas, 3 main areas. First one is in robotization, second one is in functional safety, and the last one is in virtual validation. So we created together with Flanders Make the agricultural vehicle automation project with 2 core goals. The first one is to create a research platform that should be relevant for Zedelgem machinery to collect the required research data and also operation data, operation information, and demonstrate the feasibility of the eventual autonomous operation on this platform. Second one, while we were writing, we found some key areas where further research was needed. And these we call the technology blocks. These should provide the basic technology and also give us the expertise to determine the further R&D roadmap to autonomous operation for our machines in Zedelgem. Secondly, those technology blocks should give input to a selection of the common architecture and components, which we will then communicate with the core R&D system. At the end of the project, we foresee an integration phase where technology blocks that were successful will be integrated with the research platform. And also technology blocks or software modules from non-AVA research will be integrated together with the other technology blocks on the same platform. Why did we select Flanders Make? As Chris Ganseman already introduced, Flanders Make in their OHE project created an automation kit which is portable to other off-highway applications. As you can see, those black boxes, the system and the power box from their autonomous tractor here ported on our own grape harvester platform that we're using in the AVA project. We had a successful past collaboration on automation projects. We see a clear ambition at Flanders Make to extend autonomous activities and expertise. And Flanders Make also created a relevant roadmap, including off-highway and work functions. Then we have 3, as I said, 3 main research questions, which will lead to technology blocks that we will incorporate in our demonstrator. The first one is, what should the approach be toward mapping and sensor fusion? Which approach is robust enough for agricultural machinery? We work in very challenging conditions in a visual degraded environment with a lot of dust. With changing lighting conditions, our machines operate 24/7 in all weather. Our operations introduce a lot of vibrations on the machine. which are sometimes challenging for certain sensors, and we sometimes have an unstable GPS signal. Still, we want to be able to create a clear point cloud and a clear map that we can use for navigation. So therefore, we envision a sensor fusion of sensors of different principles to a map that then can be used for robust navigation. Secondly, we have a question towards functional safety. How can we make our system certifiably safe if we will take it to production after this project? And two main questions there are, how can we set up an appropriate engineering framework or adapt our existing engineering framework for designing future functional safety and operational integrity for autonomous vehicles? And what are the implications of the functional safety standards on our electronic architecture and component selection? Then a last technology block is on the simulation of agricultural vehicles and in their environment. As you know, in the automotive space, Waymo, Tesla, and so on are driving millions of miles in a virtual environment and are training their neural networks and controllers that way. But these tool sets are not easily adaptable for an agricultural environment. And the question now is, how can we select and adapt this tool set so it can be useful for our case? There are three core uses for these kind of simulation tool sets. The first one is the development of perception and obstacle detection. There are not so many sensing models for crop existing today. So how is the interaction of waves of sensors, for instance, microwaves or laser light waves and infrared waves? How are they with the complex geometries of crop and complex properties, for instance, in the microwave domain? How can we make a photorealistic rendering of this environment for neural network training for camera data? That's certainly not easy in the case of crop. Then a second goal of these toolsets is accelerated development and testing of controllers. We have to make sure that this toolset can interface with our existing vehicle dynamics models and with soil and crop engagement models like the one you see below. It's a discrete element model for a tillage operation. Lastly, the increased coverage of tests that is needed for functional safety development. That will probably require augmenting the test data set. We will probably never be able to cover the entire domain that we need for functional safety with actual physical tests. So therefore, we would need to generate a larger data set with these simulations. But that also requires that we can automatically generate an agricultural environment based on certain parameters that we can change. What will the future bring for agricultural machinery? You will see a clear diversification and also an integration of machinery. We see a gradual transfer of tasks from the operator to a highly automated system. But for quite a while still, we will see machines of different levels of automation or of autonomy in the same field. Once you remove the operator from the machine, you also arrive at a different selection of size of a machine. In some cases, the size of a machine becomes irrelevant. Also, the power pack of a machine will change, or you will make a different selection of the power pack of a machine when you operate it autonomously. And lastly, the increased integration and collaboration of machines towards swarms and integration into an entire cyber physical system. As you see a picture here of a swarm of machines and also electrified machines that work together. So that's it from my side. Thanks a lot for your attention.
Yes, thank you very much for your presentation. I would like now to share my slides again. We have one final poll for you, and that is a question about the presentations that you have just seen. You can scan in the QR code, and the question is, will you make use of the Flanders Make of highway infrastructure that has been presented by Chris Ganseman? I'll give you a moment to scan the QR code and to answer the poll. Okay, the answers begin to come in. I'll give you one more second. Okay, I think we can continue with our webinar. So we have reached now the end of the webinar. I would like now to draw your attention to the next webinar. So we are organizing another one on the 14th of May at 11 o'clock, a webinar on how to efficiently manage complexity in product design. And the second webinar on the 19th of May, also at 11 o'clock, a webinar on how to automate creation of digital work instructions. We thank you all very much for your participation and for your feedback. And we will contact you if we have raised questions that we did not answer during this webinar. If there are any other questions or remarks, we invite you to contact us. And we would like also to invite you to fill in an evaluation form. Your feedback is very important to us, and to reach this evaluation form, you can scan the QR code that is on this slide. And with this, I would like to close this session and wish you a very nice remaining of the day.